Imagine asking an AI a question. It gives you a clear, confident answer. You ask again, and it's identical. A third time, still the same. You assume it knows what it's talking about. But what if it's completely wrong? What if it just stuck staring at the same flawed source over and over? That's what researchers call a silent failure. And it's one of the most dangerous blind spots in modern AI. We usually rely on retrieval-augmented generation, or RAG, to ground models in real data. The pipeline is straightforward. Retrieve relevant documents, then condition the language model on that context to generate an answer. But traditional confidence checks only measure one thing: whether the final answers agree across multiple generations. If they do, the system assumes it's reliable. The problem is this completely misses a failure mode called retrieval-state lock-in. Lock-in happens when the retrieval step keeps pulling the exact same defective context. This usually manifests in one of two ways. First, the system finds nothing semantically useful, so it quietly falls back on its parametric knowledge and confidently states a hallucination as fact. Second, and even trickier, it might retrieve a perfectly coherent set of documents that are just fundamentally wrong or misaligned with the query. Because the retrieved context never changes, every generated answer stays consistent. The model isn't uncertain. It's just consistently wrong. To fix this blind spot, researchers stopped treating confidence as a single scalar value. They decomposed it into 3 independent diagnostic layers that must be evaluated separately. The first layer is answer consistency. You generate multiple responses under controlled temperature settings and check for actual semantic disagreement. The second is evidence alignment. This uses a neural natural language inference verifier to compute entailment scores between the generated claim and the retrieved context, explicitly flagging contradictions that surface-level agreement misses. The third layer is the retrieval state itself. This audits the actual search trajectory to verify whether the system landed on a structurally sound, relevant source, or if it got anchored to a dead end or irrelevant cluster. When they tested this framework across multiple question-answering benchmarks, the results were stark. At a standard sampling budget, nearly 60% of the system's errors were completely silent. Traditional metrics flagged nothing. But when they cross-referenced the evidence alignment and the retrieval state, those silent errors lit up. The model was consistent, but the retrieved passages either contradicted the answer or led to a completely unrelated topic. This decomposition forces a much stricter decision rule. Instead of accepting an answer based on agreement alone, the system now requires all 3 checks to align. The answer must be consistent, the evidence must entail the claim, and the retrieval path must be structurally sound. The trade-off is real. This rule only certifies about 8% of outputs. But those certified answers are correct over 91% of the time. In highly controlled clinical evaluations, that precision hit a perfect 100% under automated scoring. Though researchers are quick to note this is an upper bound, and human validation remains absolutely non-negotiable before real-world deployment. So decomposing confidence catches the symptoms. But what about the root cause? Traditional RAG struggles when a question requires connecting multiple facts, scattered across different documents. The model just hopes the right text snippets get pulled together by chance, which is a known limitation of dense vector retrieval for multi-hop reasoning. That's where GraphRag comes in. Instead of dumping raw text chunks into a vector database, this approach builds a structured knowledge graph. You take a corpus, split it into overlapping segments, and use a language model to extract entities and relationships. These get stored as nodes and edges in a graph database. The team tested 2 extraction strategies, one guided by a strict domain schema like medical ontologies, and another that freely maps connections for general knowledge. Once built, the AI doesn't just guess which snippets might be relevant. It traces multi-step reasoning directly through the graph. If a question requires linking 3 separate facts, the system walks those paths explicitly, step by step. But here's where the experiment gets revealing. GraphRag doesn't automatically guarantee higher raw accuracy. In fact, when the graph is incomplete, or the AI latches onto the wrong starting node, it falls into a structural version of the same lock-in problem. It keeps following the same incorrect path, generates the same wrong answer, and stays completely confident. To catch these failures, researchers adapted their diagnostic framework for graph-specific mechanics. They kept answer consistency and evidence alignment, but replaced the generic retrieval audit with a metric called graph path support. This performs a structural subgraph match, verifying that the actual reasoning trajectory in the knowledge base aligns with the generated conclusion, normalized against the question's required hop count. It's essentially a structural proof check. When these signals align, the system can flag high-risk outputs before they're trusted. The key takeaway isn't that GraphRag magically outperforms traditional retrieval. The raw accuracy gap is often small, and sometimes statistically indistinguishable. The real breakthrough is visibility. By mapping out how the AI reasons, highlighting when evidence clashes with a conclusion, and verifying that the reasoning path actually exists in the knowledge base, we can separate genuine confidence from dangerous overconfidence. When we ask an AI to solve complex problems, we expect either the right answer or an honest admission of uncertainty. But when it confidently delivers a wrong answer, and doesn't even know it's wrong, we need systems that can audit their own process. Agreement is not accuracy. Confidence in AI isn't a single switch you flip. It's a layered investigation. And sometimes, the most consistent answers are the ones we need to question the most.